Hello, and thanks for using TickBoom. In this video I'm taking a look at question 2 from a series of 6 questions that are investigating how we can calculate volumes using calculus. In question 1 we took a look at the technique of using slices, and in this question 2 we're going to take a look at the technique of cylindrical shells. So if you haven't had a look at question 1, it might be helpful to just get a bit of background and take a glance at that. Here I'll work through question 2, which says the region bounded by y equals x squared bracket b squared minus x squared on c squared, the region bounded by that curve and the x-axis in the first quadrant is rotated about the y-axis. Use your values of b and c to find the volume of the solid formed. And as I mentioned in the first question, all of these constants, a, b, c, and so on, I'm just going to leave them as constants and not actually insert values, but the students who got these questions would have been given values of these constants to then finally get a numeric answer. But I'm just going to leave it in generic terms, and you could insert, in theory, whatever values you wanted to convert it into a number. So for this question 2, like I mentioned in the first video, it's always helpful to draw a diagram. The curve we're dealing with here is y is equal to x squared bracket b squared minus x squared on c squared, and that's kind of a bit hard to picture what it will look like. So we'll probably need to do a bit of preliminary work just to chart this. I think the key will be to work out the x-intercepts and any turning points in the first quadrant. So if I start with the x-intercepts, we know that will happen when each of these bits is 0. So when x squared is equal to 0, and when b squared minus x squared on c squared is equal to 0. So here we'd get x is equal to 0, and here we'd get x squared on c squared equals b squared. So x squared equals b squared c squared. So x would in theory be positive negative bc, but again we're only looking in the first quadrant, so that would just be the positive answer, bc. So there are intercepts. The question is there going to be any turning point between these two x values? So we could take a look at the first derivative and see when it's 0. So I'll just, if I look at turning points, it might be helpful just to write y to expand these brackets. So we'll have y is equal to b squared x squared minus x to the 4 on c squared. So if I differentiate that, we'll get, differentiating with respect to x, we get 2b squared x minus 4x cubed on c squared. And then if I factor that, we'll get x 2b squared minus 4x squared on c squared. So this will be 0, so y dash will be 0 when either of these are 0, so x is equal to 0, and 2b squared minus 4x squared on c squared equals 0, so that would be 4x squared on c squared equals 2b squared. So if I bring that up and c squared up and the 4 down, we get x squared equals b squared c squared on 2, since the 2 on 4 would become a half. So we'll get, again, we're looking only at the first quadrant, so only the positive solution would be bc on root 2. And bc on root 2 will be between 0 and bc. So we'll kind of, we will have a turning point between our two x-intercepts in the positive of the first quadrant. So maybe I'll turn over to just draw this up. Again, the curve doesn't need to be perfectly drawn. We just need it good enough so that we can kind of visualize what's going on as we rotate around the, in this case, the y-axis. So if I just get our Cartesian plane going. So we'll have x and y and 0. And we know we've got an intercept at 0 and an intercept at, maybe I'll just put it here. I'll call this BC. So we've got an intercept there. And we've got a turning point at BC on root 2, which is some point between here. Exactly where it isn't entirely important. It's not BC on 2, so it's not halfway between. So wherever it is not a huge deal, but the idea is that the curve, again, is it going up or going down? Technically, I could kind of find whether it's what kind of turning point this is, but you can kind of see we're dealing with x squares. I guess it depends on, could depend on the b's and c's, but could depend on the relative value. But let's just draw it like this. I think it's not going to have an impact on the volume in any case, but let's say it looks something like this. That's kind of what the curve will look like. Exactly what it looks like will actually depend on the values of B and C and their relative value. But let's just say, for our purposes, this is what it looks like. So this is y is equal to x squared b squared minus x squared on c squared. That's the curve. Now, the technique of cylindrical shells, it's kind of similar to slices. If we're rotating about the y-axis, what we would do, maybe I'll get another color, we'd kind of draw, again, we're picking here a line, we're picking a point, and we're going to rotate it around the y-axis, and we're going to find out what would the volume result from there. And then we'll keep doing it for every line and add it up to eventually get our volume. And I like to think of this, if I just kind of draw up, I'll just first draw up what we're dealing with. So if I'm going to rotate it, what we'll kind of get is this cylinder. And the idea is that, I mean, this cylinder will have a certain thickness to it, and just like with the technique of slices, we want the thickness to kind of get smaller and smaller and then add up what we're dealing with. I like to think of this technique is, if you imagined paper mache, if you've built something with paper mache, maybe in primary school or even high school, you might have used paper mache in art or whatever subject. You get really thin pieces of paper, like newspaper, and you keep layering it on top, and if you do it enough, a volume starts to build. We're essentially doing that here. That's what this technique is. You could think of getting very thin layers of newspaper, and the newspaper, the dimensions of it will kind of be what they need to be so that you eventually follow the specific curve that we're rotating here. So maybe you find that analogy helpful. If not, don't worry about it. But I think it kind of helps me to picture what's actually going on. It's like we're building a paper mache piece of art here. And so now we want to think about what are the dimensions of this cylinder. So if you kind of took this cylinder and kind of unwrapped it flat, you'll end up with essentially a rectangle. And the rectangle will have kind of, it's a prism, but the width of it is getting ever smaller. Think of a very thin piece of newspaper. Technically it has a width, and that width is a movement in x, or a change in x. Now what's the height? Well, the height is just whatever the y value was at the certain point. That's how high our kind of piece of newspaper needs to be. And in terms of what's the length, as we unwrap this, this cylinder, effectively the length of it will be the circumference of this circle. And the circumference of a circle we know is 2 pi r, so 2 pi times the radius, and the radius will always be whatever our x value was, so it's 2 pi x. And that's kind of typically the technique if we're rotating around the y-axis. The volume of this cylinder would be the area of the face times the height, so it would be y times 2 pi x times dx. And if we add it up, we'll get our volume. So here we can say that the volume will be equal to, and again we're going to have integration, and we're going to be integrating here because we're doing change in x, we're going to integrate between the x values that we're concerned with. So it will be between 0 and bc, and it's going to be 2 pi x times y, and we have y in terms of x, and because we're going to differentiate integrate with respect to x, we should write y in this form. So it will be times x squared bracket b squared minus x squared on c squared, and then times dx. And again, just like before in question 1, once you've visualized what you're dealing with and you've developed your integral, it then just becomes a question of integration. And I'll just simplify this, but we'll see it's not going to be a particularly difficult thing to integrate. So I could probably bring out my 2 pi, and then we'll have our integral between 0 and bc. So we'll have x cubed times this, and maybe I'll expand this bracket. So we'll get b squared x cubed minus x to the 5 on c squared dx. So let's just integrate that. So that's 2 pi, and we're just using a basic rule of integration. Add 1 to the exponent and divide by the new exponent. So we'd get b squared x to the 4 on 4 minus x to the 6 on 6 c squared, and that's between 0 and bc. So let's just insert that. So we'll get 2 pi times b squared times bc to the 4, which would be b to the 4 c to the 4, and that's going to be on 4, minus b to the 6 times c to the 6 on 6c squared, and then minus, it's going to be 0 minus 0. So that second bit drops away. So we'll get 2 pi times b to the 6. So we'll get b to the 6 c to the 4 on 4 minus, and this c to the 6 and c squared will simplify. So b to the 6 c to the 4 on 6. So we've actually got same term, we just need a common denominator. So that would be 2 pi, common denominator we could get of 12. So that would be, oops, that's meant to be a b to the 6. So we get, to get this on 12, we need to multiply top and bottom by 3. So 3b to the 6 c to the 4 on 12. Here we need to multiply top and bottom by 2. So 2b to the 6 c to the 4 on 12. Kind of running out of space, so maybe I'll just keep going this way. So 3 minus 2 is 1. So that's going to be 2 pi, but then the 2 on 12 will cancel. So we'll just end up, this will just be equal to b to the 6 c to the 4 on 6 pi, can't forget the pi, and then units, so units cubed, can't forget our units. So we haven't been given units, so I'll just write units in general. But that's it, that's kind of how you tackle that question. And if you had a specific value of b and c, you could plug it in to get this in terms of a number. But the key to this technique was understanding with cylindrical shells, we're picking lines of a certain width that we want the width to get smaller and smaller. We rotate it around and we get this shell that we then unwrap, and then we do it between our two points, and we would get the volume. And as I mentioned before, you may find it helpful to picture this like building up a paper mache volume. Even though the newspaper is very, very thin, if you do enough layers, it starts to take shape. So that's basically what's happening here. So hopefully that made sense. If you did find that explanation helpful, please be sure to give it a like. And if you're someone who wants to keep their finger on the pulse with the kinds of questions other students are struggling with, please be sure to subscribe to my channel so that you can stay in the loop. Alright, tick boom.